are like waves. Some appear like a cycle. Some are repetitive, are one time. Each one haunts our minds without any tangible result. Many times we feel problems overpower us. We wonder, how do we get out of it? Think for a while, organize the problems in our mind, streamline for identification, look for direct solution with pen and paper. It's not an attempt to solve, but a preparatory class. Just reduce the the ripples and smoothing it. So that solution would be easy. Arrange the problems like a file rack and analyze it rationally, which can pave the way for solution from oscillating mindset to a disciplined approach, from waves to straight lines, from recurring thoughts to direct solutions, like alternate current to direct current. All right. This is a poem by a guy from Cuttack, Odisha, which I'm pronouncing it completely wrong. That's some Indian city. And Kishore Kumar Das, whom I don't think is anybody famous, but hey, this is what happens when you look online, try to find something.
He's famous now.
Fair enough. He's famous now. I don't know. You know what? I should reach out to him and see if anybody's ever read that poem on any show.
You should.
I should, because it's one of the few poems out there that talks about ACDC, and I don't mean the band, although that'd be great.
TNT. I'm dynamite.
There you go. So, was going to spend a whole show talking about the band, but that would not be related to this SG2 on Space at all.
Yeah.
Instead, if you're watching this, we're actually talking about, we're planning to talk about alternating current, direct current, what that means, and like essentially some history behind it and so forth. But before we dive into that, what are you watching?
What are you watching?
Yeah, what are you watching? SG2 on Space, the only weekly space show every Wednesday night, 6:30, 7 p.m. Hopefully you're going to facebook.com/The Shen Show and Sports Show, patreon.com/SG2 on Space. This is currently episode 132. If you're watching it live, it's June 15th, 2022. All right. With that said, let's well, Dr. Leonard Kramer is already on, and I see you have a lovely candle burning in the background.
Yeah, Jay Nicole said it was for ambiance.
Yes, that's actually great. This is a different background than what you normally have. So wonderful. All right, so normally I don't want to just like dive into a bunch of videos all at once. Let's hear what you have to say. All right. First of all, what is okay? I could talk about direct current and alternating current, but let's start with something simpler. Like all this is related to electricity, right? So what is electricity?
What is electricity? You know, I guess that's not a question that's asked very often, is it? So electricity, I will come up with a definition. So that is the process, or it's a current of particles called electrons, usually, that we can give some energy to and use for useful things generally. So it also manifests naturally as lightning and in space physics regimes as well. So we can do things with it, and it has two properties. It has current, which is the amount of this substance that's moving through a conductor, and it has voltage, and voltage is very much akin to pressure. And I guess probably people have heard that a lot, and it kind of doesn't really quite ring right somehow. It's not intuitive, but voltage, when you say voltage, it means it effectively means the amount of pressure, how hard the electricity is being pushed. And amperage is used in units of amperage, called after a French physicist named Ampere. So, but yes,
I was gonna make an analogy. So I'm using this analogy because normally I tutor physics students, and they're frequently confused. And so I just compare it to water going through a pipe.
Yeah.
And I say the current is basically the flow rate of the amount of water, the volume of water you can see here. So higher current means
Yeah.
more water or more electrons per second, let's
Yeah.
say.
Yeah.
So and
Yeah,
then
I was
go
going to
ahead.
say, the analogy is very close because, the water is not a very compressible liquid. In other words, so you can raise the pressure on water very, very high, and it won't change its volume very much. And although you can't see it, electricity has a similar kind of property, having to do with electric charge. So
Yeah.
electrons have a negative charge, and the ions or protons have a positive charge. It's usually the electrons that are moving, and you can't put a lot of charge on something. That's almost like increasing the volume of a substance. So
Right.
a little bit of an esoteric, maybe a little subtle point, but
Well, like current is I mean, as just explained, you can kind of relate it to the flow rate of, in this case, electrons or charge flow
you
rate.
betcha.
The voltage, I like to use a comparison of, okay, so Leonard, you said like pressure. I would venture it's more of a, so I use the analogy of like water falling down a hill or being raised up a hill, like the potential difference, right, between 2 points.
Well, now, yes, I mean, the water in a water tower is at very high pressure because of
Exactly.
the height.
Right. So I'm just using that physical comparison. Obviously, for electric circuit, you're not talking about physical heights or like literal amounts of pressure. You're talking about your oh my god,
Yeah, let's leave it
the,
like that. I mean,
the potential
there's all kinds of
energy. Right.
interesting things that you could get into, but
It's a difference between potential energy per unit charge at two different
it
points.
it it it
Exactly.
is. That's what it
So,
is.
yep.
Yes.
So for anybody who's really confused, just think about it like water falling down a hill or whatever from
Yeah.
the water tower. So the water tower falling from the top, the water falling from the water tower down
Uh-huh.
here would be from high potential to low potential.
Right.
So you have what's known as a voltage, which is actually the
Okay.
difference between the two.
Yeah. Now
So,
here's a practical thing about that. Okay. So in the United States, the voltage is well, I should say in North America, voltage in a house is 120 volts, and we'll get into it being alternating current, but it's at 120 volts. In Europe and many other parts of the country, of the world, the voltage is much higher, and there's some advantages to having higher voltage because you don't need as much current to flow, and the current is what causes the heating and the losses, and so
mhm.
um, we're sort of stuck with 120 volts because we have a 130-year-old system when that was developed,
It-
and the rest of the world kind of followed the United States. So what are
uh,
we going to see? What are we going to see here? Let's see it.
this is not actually the right video.
Uh-oh.
I was hoping to pull
Heads
up.
will roll.
Do we still want to play this now? We can play that in a little bit, but I wanted to actually talk about the historical aspect, right? Like
Okay.
you just mentioned, in regards to how DC current was developed here. So, um,
All right.
like, for instance, if we take a look at this, okay, let's see what we have here.
Of the generator. Battery cells also produce direct current. Electrons flow from minus to plus. Edison built hundreds of DC plants around the world. He realized that there was a huge market for electric light. But there was one technical problem he had not resolved. The electricity lost energy as it traveled through the wires. Once the wires from the generator exceeded 2 kilometers long, there was not enough electrical energy left to turn on a light bulb.
Right.
Every customer had to be within 2 kilometers of the power plant.
Which is pretty ridiculous. All right,
Yeah.
not sure what that ad is about, but you see, that is
Yeah.
a huge problem.
That was kind of what I was getting at. Is that if they could raise the voltage, if you can raise the voltage, yeah. Jay Nicole just put OMG, but so just see message there. But anyway, so if you can raise the voltage, then you don't need as much current to transfer the amount of energy, right? And so that was the
last
real
year
problem.
I paid nothing for electricity,
Uh-oh.
and I actually made money.
So that there's an interplay as
This
the reason we
phenomenon
brought
was
it up in terms of current and voltage is because what do you call it? Joule's law is voltage times current, V times I.
How about Ohm's law?
Well, Ohm's
I
law,
like
yes.
saying it.
Well, no. I'm talking about Joule's. Okay, I'm talking about the power law. There's
Oh,
two laws,
power.
right?
Okay, it's voltage times current. Yes.
Right, because that's
right.
what's important in terms of how much we want to
Mhm.
go from the generator to our home, right?
Right.
So
So if you increase the voltage, then you can get the same amount of power at a lower current, and current is where you lose energy. So if you have high current, that's a bad thing. And so this manifests in power lines. And so these big power lines on these pylons that you see in the countryside and in the urban areas, they're at very high voltage. I don't know precisely. It's something on the order of tens of thousands of volts. I'm not kidding. Something like 20,000 or 30,000 volts, and then it's stepped down. It's converted to lower voltages so that we can use it safely in the house.
Hold your horses. This is
There.
where we need to talk about alternating current, right? So direct current was you have the same volt like what Edison had originally set up. It's easy to understand. Like you have a battery, you have a circuit, like same voltage, same current. Let's talk about let's put this up and we can talk about Ohm's law, Joule's law, and what the heck is alternating current. So let's see if we can play
would
this.
solve the problem. There is a way to do this. We can rearrange Ohm's law to state that R equals V over I.
Wow, that's
substituting V over I for R in Joule's law, we get this. Power equals voltage times current. Here is what this means. Low voltage and high current can produce exactly the same power as high voltage and low current. 100 amps times 10 volts represents 1,000 watts of power. 2 amps times 500 volts also represents 1,000 watts of power, with the advantage of a small current traveling in the wire. Edison knew that higher voltages and lower currents would resolve the line loss problem, but high voltages were dangerous. There had already been some deaths when experimenting with this solution. It was not possible to safely deliver electricity at 1,000 volts or more into homes. He had no solution to the I²R problem. The solution that Tesla proposed, a solution rejected by Edison, was to abandon direct current and develop an electrical grid using alternating current, AC.
Yay.
Unlike DC,
well, let's continue with this little chart here.
Alternating current doesn't flow constantly in the same direction. It changes direction, surging back and forth. Alternating current is easily produced with a special type of generator, and AC has some very interesting properties. This surging back and forth motion of the current produces electromagnetic radiation that can induce current flow in adjacent but unconnected conductors. Tesla understood this radiation and perfected a device capable of changing voltage and current in an electrical system, the transformer. This changed everything. Suddenly, it was possible to deliver electricity hundreds of kilometers using high voltage, low current transmission. The low current reduced line losses dramatically. The wires carrying the high voltage were suspended on towers at a safe height. The final step in this brilliant solution occurred when a step-down transformer converted the electricity back to a less dangerous low voltage with higher current for use in the homes and industries of the community. The relatively short distance from the transformer to the home meant that line loss from the higher current was minimized. Tesla had found a solution to the line loss problem. Edison realized he had a problem.
And then Edison tried to kill a bunch of elephants, which is what it was going to show. We don't
I don't
have
want to
to
see
show that.
elephants being killed. I love elephants. No elephant
Well,
should ever die.
His point was showing how you have
That it's
really high
dangerous.
voltage, it's dangerous.
Right.
But as the video indicated, we put those really high up, right? I mean, nobody's going to climb up and start grabbing.
Well, we've been doing it for a long time. So, but yeah, I mean, our audience, can consider that those power lines way high up there. There's 3 wires. They're very high voltage, and they're stepped down to the line voltage that we have into the house with those big cans that you see on the power poles. And so it's really interesting. I don't know. I think it's neat.
It is really interesting.
One of the things I've observed is that if I travel in Europe, I can use the same transformer to plug in my computer. Okay, it's the technology exists where I can plug the transformer, the little thing that you plug into the wall. If I do it in Europe, the voltage is 240 volts there, and the transformer runs cooler. It doesn't get warm at all. Whereas in the States, it gets warm, and so that's a real manifestation. That's a real life kind of manifestation of that issue. Also, the little USB ports that we have, I got some here, the USB power, that runs at 5 volts. And in order to charge something, it generally, the transformer runs kind of warm. I think probably everybody's observed that. The little blocks that you plug into the wall, they run pretty warm because there's a significant amount of current that's flowing in those little wires. So they have to make it 5 volts, for safety. Although you can still shock yourself with those things. They have some technology in there that limits the current and that sort of thing. But also the length of the cable actually makes a difference. I think maybe some of our listeners have noticed that it takes longer to charge things with a very long cable. And so probably belaboring that too much, but it's something I've noticed. And so yeah.
Well,
So
I mean,
AC is cool.
it makes a lot of sense. So, I mean, clearly, DC is still very frequently used.
Well, DC, that's important. So the laptops and whatever are using those because they have batteries, and
right,
so
like my phone,
the phone, yeah. So that uses DC, but the reason they use that DC is because the technology for batteries is a chemical process that produces a DC current. And there isn't any really practical reason to step down the voltage or step up the voltage for those kind of applications. So
just an indication, this is an example of a battery, right? So you have I think everybody has used.
Yeah, well, it's good that you're showing that for the people who've never seen a battery.
Here's a positive, and here's a right here, negative.
Oops.
This requires 2 AAA batteries, so it forms a circuit, right, going through. So you plug this in. This is pure DC. So the current is going one direction. The voltage is not changing either. And essentially, here, look, here's a light. Wonderful.
Oh yeah.
Okay. So and same with our phone, right? Except, instead of that battery, it's a phone battery, which is why for the phone battery, as Leonard pointed out, you need to charge it with a USB cable. So when I plug this in and I plug this other one into one of those little blocks, like you said, that's like that's a transformer, right?
That's a transformer because what's 220 volts AC is going in, and something like 5 and a little bit volts DC is coming out. The DC is coming out pulsed. There's something called a rectifier in there, which is like a it's not like a transistor. It actually is a transistor that only allows the current to flow significantly in one direction, and so that's how
Right.
that's done.
Well,
In the
I
old
mean, there's
days,
two things happening. One is that not only, yeah, go ahead.
I was just going to say, automotive applications also use a battery to start, and now we have electric cars, and so those are all using chemical sources of electricity, a chemical reaction that produces electricity, and it's also rechargeable. And so DC current works for most automotive applications. Although interestingly, I don't know about late, in the middle, well, first quarter of the 21st century is where we are now. But in the old days, at least, there was a big battery in there, and there's also an alternator in your car. So the alternator is a fancy name for an AC generator. So the current alternates, but it needs DC. So there was always this technology called a rectifier, which turned the AC into DC in order to charge the battery. And I believe that's still a thing, but
Right.
I couldn't swear to it. I haven't put my head under a car hood for
that
10 years.
That makes perfect sense, actually. I'm gonna have to look into that later. So there's both a rectifier as well as a transformer. Let's see. So this video that was attempted to be played originally. Let's see if we can get this up. This is kind of cool. This guy built this device. It looks kind of unsafe in a little bit.
It looks like a torture device or something.
Look at this. You can compare what happens when you do 220 volts AC versus 220 volts DC. Okay, let's play.
Oh yeah, let's look at it.
There's.
All right, he closed the switch. Oh, something's heating up there.
Yep. So it's like fluorescent lights, right? Now he switches to DC and watch what happens. Okay. All right. So it lights up, and then he tries to disengage.
Oh, that's another thing that happens.
That does not happen with AC. So
right. And the reason for that has to do with the induction of the wires. The wires, and when you have a DC current, they build up a big magnetic field. I mean, I think you know about that current creates a magnetic field, and that stores some energy out in the space around the wire. And then when you disconnect it, the current wants to keep flowing. It's almost like it's got inertia from this magnetic field that's collapsing. I noticed that he actually made it worse by separating the wires. If you have the wires close to the two wires that there's a forward current and then the return current. If you keep the wires close together, you won't have that problem. But that was actually pretty cool. I like that. But you don't have that with AC because the current is flowing back and forth quickly, and so actually the electrons are not actually moving, as much as you might imagine, and so they don't build up a magnetic field. There's still a magnetic field, but it's sort of buzzing. It's like humming at 60 hertz.
So just a note, I thought this was interesting. Like for all our power devices, that's not like requiring a rectifier. So like for instance, my lamp over here, which you cannot see. How about this one? This lamp.
How about my lamp?
Or wait, that's a candle.
Yeah.
You're totally not using electricity.
That's right. Then that's sunlight coming through the window here.
Right. Okay, so this lamp, it's directly connected. So this is running on AC. I mean, it's obviously stepped down. So this is not DC. And yeah, so electrons are actually, the current is actually flowing in one direction and back very rapidly, like what, 60 hertz or something?
60 hertz, yeah.
Mm-hmm. So it's like 60 times in 1 second. So really, this light should be like kind of flickering, I suppose, but our eyes don't notice it because it's going so fast.
Yeah, I think that's right. I think it probably is. It is flickering, but also there's probably enough. The filament is probably hot enough that it continues to glow even with it. So it doesn't actually flash on and off. It's just that it gets very hot. It keeps it hot. And then there's similar technology nowadays. We have LED bulbs that have some, probably, I don't know, okay, but they probably have a little bit of circuitry in there to keep it keep it constant.
I want to conclude with talking about the Earth actually generating its own electric field as well, electromagnetic field, due to the liquid. A lot of our audience, and definitely you, Leonard, knows about our molten lava.
Well, okay, so there are currents that are flowing in the mantle. I mean, in the core of the Earth, in the metal. It's a liquid conductor, and it's of planetary scale. Okay, so the conductivity of that material is limited enough that it effectively carries the magnetic field along with it. So whenever you see magnetism, there's a current somewhere, and we could actually talk about that. There's a lot of interesting things having to do with magnetism and currents. But every magnet has something to do with electricity. Even solid magnets. Just the magnet refrigerator magnets have something to do with electricity. Yeah.
Something to do with electricity.
A layer of liquid metal.
Let's play this real quick.
This generates electric currents that then produce magnetic fields that all together encompass the entire planet. Called a geodynamo, this process causes Earth's poles to attain positive and negative charges, turning the planet into a giant electromagnet. This phenomenon also creates a protective layer around the planet. It shields us from the most harmful.
That's a very simplified explanation, and
I wish that she had not said charges.
Fundamental force of
I
electromagnetism.
kind of bristled a little bit, so
I could tell,
because it leaves you with the impression that there's electric charges or something. Okay, but that's not what's happening. Okay, so the magnetic field is not a manifestation of an electric charge. Okay, so it has to do with current, a loop of current. So if you have a wire and you put a current and have a loop of wire, then there will be a magnetic field through that. So yeah. Anyway,
you know what? I think what we can do is talk more about this.
Yeah, we've talked about it before, and I find it a very interesting kind of thing. And I think we've talked about planetary magnetism and that
we have. I'm merely relating the fact that us humans are not the only ones that's generating any kind of
Well, that's right. I mean, and there is a free air electric field that's not related to the core of the Earth, but has to do with thunderstorm activity.
That's another thing.
That's a thing. That's a very interesting topic to talk about. That there's a worldwide global electric circuit that is driving a voltage difference between the ionosphere and the surface of the Earth, and it correlates with global thunderstorm activity.
We talked about this.
So that's a very interesting kind of thing. Also, it occurs, in nature. I mean, well, not only thunderstorms and so forth, but there's certain kinds of fish and eels and rays that produce an electric field and use it to shock their prey. It was noticed in ancient times. It was a very in fact, I think that the word electron comes from a word for a certain kind of fish. I could be wrong about that. Somebody will have to check me on it.
Let's talk about more of that next time. I want to go on and talk about.
Oh no, we're out of time. Oh my God, where did the time go? This was so okay.
Know.
Farmington, Missouri. That's where they see all the best UFOs. Let's do it.
Let's see what happens here. I will explain to you what's happening, or you can tell me what's happening.
Just a few weeks ago.
I know.
Farmington, Missouri.
So this was reported by Melissa Bates of Farmington. She saw a bright light coming in and out of focus for an hour, and it was just days after her friend apparently saw a similar glow in the sky. So May 16th, this was shot then, right? She was left baffled as she tried to figure out what the ball was. She said that the object did not move with intent, and several people were spooked on seeing this in the night sky in Missouri. So, what could it be?
What could it be?
Yeah,
Could be an alien spaceship.
I can't believe you're agreeing or
I didn't agree with anything. You asked me what it could be. It could be an airplane.
This is really like not terribly convincing because it's so far away, and I can't.
Yeah.
I have no idea what is happening.
What are those little white streaks that are in the thing in the film? Look at there. You see there? That's actually much more interesting. What is that?
What? I thought that was like a bug or something of some kind. That's my
I think it's. I don't know.
All right.
Please.
No
like-
need to
like
subscribe
and
to that guy.
Yep.
All right.
Okay.
Well, UFO Casebook has some really bizarre and
Yeah.
sometimes really not so convincing videos, but
Pretty fun.
any case, that conclusion to me was I don't know what it is. You need to take a better video.
That's
so-
what we seem to always say. I'm I've never been. I want to be abducted. Actually, I don't want them. I don't want any probes put in me. But I I want to meet. I want to know what they're doing. I had a friend that once said that the aliens were coming to Earth and dissecting cows and stuff because they were bad medical students. I think I've told that joke before.
You told me that. Especially there was a video I showed you once about apparently cows being found wandering around, and you made that joke, and I was like, look, this is what they're doing. So literally. All right.
Anyway, I love it.
But in that sense, look up because you never know what you will see. Who knows?
Right.
You might see some bright lights.
Yep.
But
I think I mentioned I saw the International Space Station the other night.
That's a more likely possibility.
Thing that you can see.
Yeah, for sure. And it's amazing that you can see so many things with your naked eye. But we're trying to close.
He said naked.
Yes, wow, way to go. Yes.
Yep.
Tune into SG2 on Space every Wednesday night, 6:30 to 7 p.m. U.S. Central for our live show. And of course, you can go on facebook.com/StationShow to watch all past episodes. And if you really don't want to see Leonard, go on YouTube and search for SG2 on Space.
But why would you not want to see Leonard? I mean,
well, let's put it this way. If you want to see earlier episodes than a year and a half ago. So,
okay.
All right. And with that, we'll be back next Wednesday. As always, support go, patreon.com/SG2 on Space. Thank you, everybody, and have a good night.
Like and subscribe, and namaste.
Namaste. There you go.
Thank you.
Does that sound like electricity to you?
Yeah. Actually, I was actually nearly struck by lightning about 30 years ago. Huh?
I said, I think you shared that story with me sometime ago.
Well, when you get a certain age, you start repeating the stories. I think I repeated about 3 or 4 stories tonight.
It's all good. Not every